Hi Laurent, so here's a quick overview of my HPLC method development or flowchart. So firstly I'll stop on the legend. You can pause here and have a read if you'd like, but I try not to waste too much time. So we start off, first we need to know our compounds if we're in the realm of polar or non-polar, and it's also a good idea to check the pKa values of our analytes. Then we go and we choose a column. We either choose a C18 or one of the other exotic columns. Then we decide if we're doing isocratic or gradient. So in the video, just for argument's sake, we'll start with isocratic. So the first thing we do is when we're equilibrating, we set the flow rate so we're really close to the maximum back pressure but without exceeding it, so maybe between 3000 and 3500. Then we go on to use 100% B. We calculate K from the first and last peak. We ask ourselves if K is less than 3. If it's not, then we stop, and our compounds probably aren't suitable for reverse phase HPLC. And if resolution is greater than 1.5, and so we answer yes to the question, then we come all the way down here and we end up at the smiley face or the goal, and that's where we usually end up, where we answer yes. But if we say almost, so resolution's at about 1.4, which is close to 1.5, we follow this darker blue line down here, and we end up going and trying to influence efficiency to improve resolution. But let's say we answer no to that question, so resolution's not greater than 1.5, then we calculate K and we assume our multiplying factor is 3. Then we determine what percentage B will give us the K value closest to the maximum, so without exceeding our K limits or our runtime limits. Then we use that percentage B in the next isocratic run, and then we check the chromatogram and see if resolution is greater than 1.5, and K should be less than 15 according to that equation that we used if we decide we want K to equal 14. So if it's yes, again we go to the goal, almost, we go and change efficiency, but if not, then we can no longer improve or change K to affect resolution, so we go and we try and affect selectivity. So the most effective way to change selectivity is changing the solvent type. So we choose another solvent type, we use a nomogram to work out an isoallotropic percentage B that we did in that equation earlier, and we do a run. Again, if we answer yes, we go to the goal, almost, we go and change efficiency, but if not, we then come and ask ourselves this question: if both peaks are separated by both solvents. And here's just an example of that. So with acetonitrile, ketoprofen and naproxen are not separated. With methanol, it's ketoprofen and Solindac. But if you look across both chromatograms, all the peaks are actually separated. So, but if we answer no, so if that is not the case, then we go and we see if we can change the solvent type again. And if we can, by all means, go and change the solvent type, use the nomogram again, and try and see if if all the peaks are separated by two of the solvents. But if we've used all the different mobile phases, then we need to go back to the start and change the column, and then go back to that blue box. But if we have said yes, then we use an isoallotropic mix of both of the solvents that separated all of the peaks. Ask ourselves again if we achieved a goal. If we have, we go to the end. If not, we ask if resolution is close. So this is like answering almost, and if it is, then we go and change efficiency. If it's not, then we try and influence selectivity again to change resolution. So the first thing I decided to do was to change temperature, see if that's improved selectivity to achieve our goal. If it has, we end up at the smiley phase. If not, we'll see if we're close. If we are close, we go and change efficiency. If we're not close, we try and change selectivity again. So we'd go here and we'd change pH. Ask ourselves again if we achieve the goal. If so, back to the smiley face. If not, see if we're close. If we are close, go and change efficiency. But if we're not, we're kind of out of options. There's no point going and changing efficiency because its effect on resolution is kind of minimal. You won't get it. If you're at 1.2, you probably won't be able to change efficiency that much to get to 1.5. So you either move to a gradient, change your solvent type, or we change the column type and now back at the start. But let's say for argument's sake we answered yes to that question, so we're almost, or we're at around 1.4. We then go and change efficiency. So here's a little bit of information for the user or for myself in the real world when I use my flowchart. The first step I decided to do to change efficiency was to change the flow rate, or I guess influence linear velocity and change the efficiency. I did this simply because I thought it was the easiest, and it may not be the most effective, but basically you don't have to swap the columns and repurge, re-equilibrate and everything like that. You can just change it on the computer. So that was my first step in changing efficiency. We choose a few increments lower than the flow rate because we obviously can't increase the flow rate, because in that earlier step we set the flow rate really close to the maximum between 3000 and 3500. So we pick a few increments below the flow rate that we're using at the moment. lower the flow rate, see if we've achieved the goal. It's also important to check runtime, because decreasing the flow rate will increase the runtime, and that could be too long for whatever our specifications are. If not, we try and change the increment again. If not, lower the increment again, and hopefully that works. If it doesn't, we then need to go and change another aspect of efficiency. Now we could decrease the column diameter to change linear velocity, but I thought that changing the flow rate changes linear velocity, so if that hasn't worked, maybe column diameter won't work either. But obviously you could get different linear velocity values by changing column diameter, so I haven't done that here, but it definitely could be done, or you could try it. There's a little information there just about why I didn't put in column diameter, because of the effect of linear velocity. So the next thing I did was to try to increase the column length, so increase the number of plates, hopefully improve efficiency. So we do that, we maybe use 200. We need to check runtime again, because a longer column will result in a longer runtime. If that hasn't worked, try change the column again if you have another column available. If not, so linear velocity and column length hasn't seemed to work, so maybe we go and try and change particle size. So we'll decrease the particle size to have to reduce eddy diffusion. Eddy diffusion. So if that's worked, again, yes, we end up at the goal. If not, then maybe we can decrease injection volume, because all that adds volume adds band broadening. If that works, we end up at the goal. If that doesn't work, then unfortunately we're kind of out of parameters to change, so we end up back at this blue box, move to the gradient, change the solvent type, or change the column. So let's say this time we decided to move to the gradient. We're back at the start here, so we've chosen the gradient method. Like in the isocratic, we need to set our flow rate close to the maximum back pressure without exceeding it. We use a scouting gradient. We look at the gradient, we calculate delta Tg and 0.25 times delta Tg. If delta Tg is less, so if we answer yes to this question, we go and use an isocratic method. We take the percentage beat, half the delta Tg, check our resolution. If we answer no, then we go across here back to this point in the isocratic method. But if we say yes, then we come down here to our smiley face and we've achieved the goal. So let's just say we answered no to this question. So we then calculate percentage B at the first peak, and we use that and change the organic range. Check if that's worked. If it has and the runtime's adequate, then we go down to the smiley face. But if it's not, then maybe we change the gradient time. And hopefully this will change the slope of the curve and hopefully achieve our goal. So we ask ourselves, if yes, we end up at the goal. If it's not, we can tinker with the gradient time again and hopefully achieve our target, or we end up at changing the organic range. And we can do that by changing it. We can have it like a few steps if we want to, and really tinker with that, just play around with it and hopefully achieve our goal. So if we do, we're back at the smiley face. But if not, we probably then need to go and decrease our column length. So this is us trying to influence K. We could have used flow rate, but to change the flow rate, to increase K using flow rate, we'd have to increase it, and we can't do that because we're already pretty close to the maximum. Or we could decrease column diameter, but again, that'll increase back pressure, and we're pretty close to the maximum. So here's just a bit of info why I ruled out those two options and went for a decrease in column length. We check if our resolution is greater than 1.5. If it is, we've achieved the goal. If not, then we can no longer influence K. So like in isocratic, we then move to selectivity. We change the solvent type. If we haven't achieved our goal, then we might need to change the solvent type again, go back to the start, try a scouting gradient. But if we almost have, maybe we can try and aim to influence efficiency by changing the injection volume, because again, all that adds band broadening. But if that hasn't worked either, we're kind of out of options and we need to try another solvent type again, change the column, or even go back to an isocratic method. So we're kind of back at the start. But if we did answer yes and we did achieve our goal, then the next step we'd need to validate the method. So there's a few steps in that I won't go through in the video. Hopefully the information there suffices. But yeah, that's pretty much the method is developed, and then we just need to go and validate the method. So thanks for all your help with the flowchart and all your feedback and everything.